In this section, we'll be looking at how to graph the cosecant and the secant function. Now, more specifically, we'll be looking at how to graph the parent function first before we graph any transformations of these two functions. So we'll start by looking at the cosecant function, and you should be able to recall this reciprocal trig identity for cosec x. And this is that cosec x is equal to 1 over sine x. So we'll be using the graph of sine x to help us graph cosec x. Now the graph of sine x looks like the following, and you should be able to recall this from previous lessons. So the first thing we'll pay attention to for sine x graph is the x-intercepts. These are the real zeros of sine x. So at the x-intercepts, we'll draw in the vertical asymptotes, and these are the vertical asymptotes for cosec x. So bear that in mind. Wherever the x-intercepts of sine x are, this is where the vertical asymptotes for the cosec graph will be. Now, the next part we'll pay attention to is the fact that sine x oscillates between 1 and -1 all the way throughout. So we'll just highlight them there for you. So we'll pay attention to this first part where y equals 1 or sine x is equal to 1. Now over here you can see the sine graph curves downwards having gone through y equals 1. The cosec graph will curve upwards going through y equals 1. And that's this first section complete for cosec x. Over here, you can see that the graph for sine x curves upwards, having gone through y equals -1. The cosec graph will curve downwards, having gone through y equals -1. Now, because cosec x is a periodic graph, these two parts, or these two sections, will repeat themselves throughout. This is one cycle of cosec x. So we'll just repeat these. So over here, it will be very much similar to what we have over here. It'll curve upwards, and over here, it'll curve downwards. And that completes the graph for cosec x. Now, if we look at the period between minus pi and pi, the period of the cosec function is 2 pi. So, generally speaking, when we draw the graph of the parent function for cosec x, we'll draw it between minus pi, and this will give us one cycle. Then we'll simply draw in another cycle to the right, and then another cycle to the left. So, moving on to the secant function, we should recall this reciprocal trig identity, that sec x is equal to 1 over cos x. So we'll be using the cos x graph to draw the sec x graph. So this is what the cosine graph looks like. And you should be able to recall this from previous lessons. So again, like before, wherever there's an x-intercept for cos x, or wherever the real zeros of cos x are, this is where we'll draw in our vertical asymptotes for sec x. And again, similar to the sine function over here, we know that the cosine graph oscillates between 1 and -1 throughout. So we'll just highlight those points there. And again, we'll just take a look at this section where y is equal to 1 or cos x is equal to 1. And we can see that the graph curves downwards, having gone through y equals 1. So sec x will curve upwards, having gone through y equals 1. And over here, the graph curves upwards for cos x, having gone through y equals -1. But the graph of sec x over here will curve downwards, having gone through y equals -1. And again, these two, what we have here in blue, will repeat themselves throughout because the secant function is also a periodic function. So we'll just draw them in now, and over here we can take a guess that it will be like this, curving upwards, and over here it'll be curving downwards, and over here it'll be curving upwards. So essentially you have these U shapes and N shapes for the secant and the cosecant graph. So now the period for this graph will be 2 pi as well. So that's between minus pi over 2 and 3 pi over 2. So this is one cycle of the graph. So generally speaking, when we draw the parent function for sec x, we'll draw it between minus pi over 2 and 3 pi over 2. So this will give us one cycle, and we simply draw another cycle towards the right, and then another cycle on the left. And this completes the parent functions for cosec x and sec x. Now we'll be looking at two key terms for the cosecant and secant function. So before we do that, we'll think about the extrema for these two graphs. Well, they don't exist. The extrema is the absolute maximum value and the absolute minimum value. And you can see, if you try looking for an absolute maximum value, there isn't one because they both go towards positive infinity. And if you try looking for an absolute minimum value, they both go towards negative infinity. So both the absolute maximum and the absolute minimum doesn't exist for this graph, or these two graphs. Now, although the cosecant and the secant function don't have extrema, we have what we call relative minimum, sometimes called the local minimum. And what we mean by that is if we look at between 0 to pi, this value here, the point that I have there, the cosec equals 1, this is the minimum value within this region. And it's not unique, it repeats itself. And you can see that over and over for both functions. And again, we have a relative maximum or a local maximum, sometimes it's referred to. And if we look at this region between pi and 2 pi, cosec x equals -1. This is the maximum value within this region of between pi and 2 pi. And again, this isn't unique, this repeats itself throughout. So these vertical asymptotes, alongside these two key terms, relative minimum and relative maximum, are important properties for the cosecant and secant function that we need to remember.
Now before we continue, please don't forget to like the video and subscribe to our channel. As a reminder, we offer private and group online math lessons on Zoom. The first session is always free. We cover all UAE National Curricula, American and British curriculums. We also have the best MSAT math test preparation course with a 50% discount for groups. So if you are interested in a free lesson, click the link in the description below, and send us a message now. Okay, with that said, let's get back to our lesson.
Before we look at the steps to draw the graph of a cosecant function, we have the general form of a cosecant function. So you should recall these values of a, b, c, and d, which are very similar to what we had for the tangent, the cotangent, the sine, and the cosine functions as seen previously. Now, we'll also have these table of values, and there'll be 5 key points to help us draw one cycle of the cosecant function. So for step 1, we work out the period, and we work this out by computing 2 pi over the absolute value of b. So please make sure you make a note of this. So step 2 is to find and plot the vertical asymptotes, and we do this by solving these two equations, bx plus c equals minus pi and bx plus c equals pi. And again, you should recall bx plus c is this bit in the bracket. Now, once we get our vertical asymptotes over here from these two equations, we can work out the period of the graph. So remember, this is one cycle of the cosecant function we'll be drawing, and this is the beginning and the end of that cycle. So to work out the period, okay, from the graph, we just work out the horizontal distance between these two vertical asymptotes, and if this agrees with the period that we computed earlier, we have a degree of certainty that we're on the right path. So we haven't completed step 2 just yet. We also need to find a third vertical asymptote, and that lies in the middle of these two vertical asymptotes. So we have that over here. So that's 3 bits of key information that we have. Now, step 3 is to find and plot the relative minimum and maximum. So we start off with the relative maximum. And again, over here, we'd have the relative minimum. So as this is the relative maximum, the graph of cosecant function will curve downwards, having gone through this relative maximum. And over here, the graph will curve upwards, having gone through this relative minimum. And that'll complete one cycle of the cosecant function. Then all we need to do is draw another cycle over here on the right hand side and draw another cycle on the left hand side. And that'll complete the graph and the steps. Now the steps to draw the graph of secant function, again, will be very, very similar to what we've just done. We have the general form of the secant function, okay, and we'll have 5 key bits of information that will help us draw or graph one cycle of the secant function. So step 1 is to find the period, and we can work this out by working out 2 pi over the absolute value of b. So this is the same as the cosecant function. Step 2, we want to find and plot the vertical asymptotes by solving these two equations. So you'll notice the first equation, bx plus c is equal to minus pi over 2. And over here, bx plus c is equal to 3 pi over 2. So again, please make a note of this, as this is different from the cosecant function. And again, bx plus c is just this part in the middle or within the bracket. So these are the two vertical asymptotes we'll get from this graph. So because this is one cycle, this is the beginning and the end of that cycle where these asymptotes are. And we can work out the period. And if we work out the period here from the graph, and it agrees with what we have here, we have a degree of certainty that we're on the right path. So like before, we also need to work out a third vertical asymptote, and that goes in the middle of these two vertical asymptotes that we worked out from these two equations. Now, for step 3, we find and plot the relative minimum and relative maximum. Now over here, we will begin with the relative minimum, okay, and then we'll have the relative maximum. So these two have swapped around compared to the cosecant function, so you do need to remember that. So if this is our relative minimum, then we know that the graph will go through this but curve upwards. And this is our relative maximum. We know that the graph will go through this, but it will curve downwards. And then once we have one cycle of the secant function complete, we draw another cycle on the right hand side and then one more cycle on the left hand side to complete the graph. So in example 1, we're asked to locate the vertical asymptotes and sketch the graph of this cosecant function here. So remember, we're looking for 5 key bits of information. So step 1, okay, let's recall the general form and the formula to work out the period over here. We'll work out the period first. So before we do that, let's highlight some key bits of information within the original function, x plus pi over 2. So if we make a comparison of this to what we have over here, we can see that the value of b is equal to 1 and the value of c is equal to pi over 2. Now, from this, we can work out what the period of this function is by substituting and replacing b with 1. So we'll get 2 pi over the absolute value of 1, which simplifies to 2 pi, and this is the period for this function here. So for step 2, we'll work out the vertical asymptotes. So these are the two equations we'll need to work out two vertical asymptotes. And if you recall from previous lessons, bx plus c is simply this part that we have within the bracket, x plus pi over 2. So I'll replace bx plus c in both equations with x plus pi over 2. So we get the following. So now, x plus pi over 2 equals minus pi and x plus pi over 2 equals pi. We solve both of these equations to give us x equals minus 3 pi over 2 and x equals pi over 2. And we'll put them over here and there. So these are the two beginning and end vertical asymptotes, and we want to work out the middle one. How do we do that? Well, if you recall from the steps we showed previously, it'll be in between these two asymptotes. So we add these two values together and divide them by 2, and it will give us x equals minus pi over 2. Step 3 would be to find the relative maximum and the relative minimum. So how do we find these two values? Well, again, just from previously looking at the parent function of the cosecant function, we know that the relative maximum, or the x values of the relative maximum, lies exactly in the middle of these two vertical asymptotes. So we'll add these two values together and then divide them by 2 to give us minus pi. And then we can work out the y value of minus 1 by substituting minus pi into this function over here to give us y equals minus 1. And then for the relative minimum, we'll add these two x values together, divide them by 2 to give us 0. And then we can work out y equals 1 by substituting x equals 0 into this function to give us the y value, y equals 1. So now that we have these 5 key bits of information filled out, we can draw one cycle of this function, cosecant. So now we have a vertical asymptote at x equals minus 3 pi over 2, which goes over here, and x equals pi over 2, which goes over there. We'll draw in the middle one, okay, which is x equals minus pi over 2, so it agrees with what we're doing. and then we have the relative maximum and relative minimum, which we'll plot in like so. So now our graph will go through this relative maximum and it'll curve downwards, and over here it'll go through this point but it will curve upwards. That completes one cycle of the cosecant function. We just need to repeat what we have here on the left hand side. Okay, so we have another vertical asymptote there, then we have another one going in the middle, and then we just repeat these two graphs like so, and then we want another cycle towards the right. So we'll have a vertical asymptote going over here. You can see this period is 2 pi. We'll have one in the middle, and again we'll just repeat these two graphs, or these graphs that we have in blue over here. So we'll have one down here and we'll have one up there, and that completes the question. So now for example 2, we're asked to locate the vertical asymptotes and sketch the graph of this function, which is a secant function. So again, we'll have our 5 bits of key information that we need to fill in, and then step 1, we'll write down the general form and how to work out the period. Now from the general form we can then see x over 4 tells us that b is equal to 1 over 4. So we make a comparison between the general form and the function given over here, and b equals 1 over 4. So because b equals 1 over 4, we can substitute into this formula here, and this will give us 2 pi over the absolute value of a quarter, and this will simplify to give us a period of 8 pi. Now for step 2, we'll try to work out the vertical asymptotes using these two equations. Now you'll recall again, bx plus c is just this part of the general form within the brackets, and the equivalent form for this function is x over 4. So I'll replace bx plus c over here and bx plus c over here with x over 4 to give us the following. And then we can solve these two equations to give us x equals minus 2 pi and x equals 6 pi. So I'll put these in over here and over there because these are the beginning and the end of one cycle of this function. So we'll work out the middle vertical asymptote because it lies in between these two. So we just add these two values together and divide them by 2 to give us x equals 2 pi. And for step 3, we'll be working out the relative maximum and the relative minimum. So again, for the secant function, it starts with the relative minimum, and over here we have the relative maximum. So for the cosecant function, they were reversed. So make sure you remember that. So how do we work out the relative minimum? Well, we work out the x value of the relative minimum by working out the middle value of minus 2 pi and 2 pi. So minus 2 pi plus 2 pi is 0. 0 divided by 2 will give me this x value of 0. We substitute this x value into this function to give us the y value, y equals 1. And we have the point that we're looking for. And we'll do something similar for the relative maximum. We add these two values together to give us 8 pi, divided by 2, and it will give us the x value, 4 pi. And then we substitute this x value into this function to give us the y value, y equals minus 1. So now that we have these 5 key bits of information, we can draw in one cycle of this function here. So we have the beginning and the end vertical asymptotes going over here and there, and then we have a vertical asymptote in the middle where x equals 2 pi, and we can plot these relative minimum and this relative maximum in like so, and then the graph will go through this point but it will curve upwards, and the graph will go through this point and it will curve downwards. And then we simply make another cycle of this graph to the left hand side like so, and then to the right hand side like so, and this will complete the graph that we're looking for. Now it's your turn to have a go at answering these questions, so pause the video before I reveal the answers. And the answers are the following.